Okay, let's talk a little bit about the graphs of multivariable functions. Okay, graphing functions of two independent variables. So just like we've been thinking about an x-y axis when we have y equals f of x, now we want to think about an x-y-z axis. So functions of one independent variable are graphed by plotting ordered pairs, x comma y, on a two-dimensional xy axis. Okay, but if we extend this into an extra variable, functions of two independent variables are graphed by plotting ordered triples, x, y, z, okay, on a three-dimensional XYZ axis. And so here's a little image about what that looks like. So just like the XY axis is divided into 4 quadrants, the XYZ axis is divided into 8 octants, where the first octant is the region of three-dimensional space where all coordinates are positive. And so just this little image here, we can think about this point right here that's graphed x comma y. If you've got an xy axis, and we typically draw it where the xy axis is kind of laying flat on the ground, and then the z axis is the one that sticks up and down out of the xy axis. And so if we have any ordered triple xyz, you can think about heading out in the x direction along the x-axis. Then you could head out in the y direction along the y-axis. And then you can head up in the z direction. Okay, and you can find out what this point is located in three-dimensional space based on an x component, a y component, and a z component. And then it's an entire huge branch of mathematics to start talking about things. There's a distance formula that's like a generalized Pythagorean theorem and all kinds of awesome stuff that we can start analyzing. We're not going to go crazy in depth with that, but I just want to do some background on multivariable functions before we start doing partial derivatives. So let's talk about this a little bit more. In chapter 1, we saw that the graph of ax plus by equals c is a line. Okay, that's just the standard. You can rewrite that as like y equals mx plus b. Okay, so that's a line. So a one-dimensional object on a two-dimensional plane. Okay, so it just has like a line just kind of has like length. Okay, but in the two-dimensional plane has length and width. Okay, and then so anyways, we can generalize this result up to 3 dimensions. And so if you have a line that's one-dimensional, if you go up one more dimension, then you end up getting a plane in three-dimensional space. So the graph of ax plus by plus cz equals d is a plane if a, b, and c are not all 0. So that's pretty much just generalizing a line and taking it into three-dimensional space. And then a line becomes a plane. Okay, and we're going to visualize that a little bit. I have a visual aid here that's going to be kind of fun to look at. So just like we find x and y intercepts to help us graph lines, we can use x, y, and z intercepts to help us graph planes. Those would be really convenient locations to find to help us kind of connect the dots and see where the plane would be graphed. The intercept for one variable, of course, occurs when the two other variables are 0. The graph of a function of one variable, y equals f of x, is called a curve in a plane. Okay, we've done parabolas and all kinds of stuff where it's a curve in the plane. But if we do the graph of a function in two variables, z equals f of x comma y, that's going to end up being a surface in a three-dimensional space. Okay, cool stuff, and we're going to get a visual aid of all of that in just 1 second. And then just to throw out some names there, common surfaces include planes, like we mentioned, but there's also some crazy shapes out there, paraboloids, which is pretty much like a parabola that you can send into three-dimensional space, ellipsoids, hyperbolic paraboloids, all kinds of cool stuff. So you guys know how much I love using Desmos to try to do different graphs and interpretations of functions. However, we've kind of reached the limit of Desmos because Desmos can't really handle three-dimensional space very well. There's like little loophole tricks to do it, but there is another software that can actually use it. Another website, Geogebra. And this is a good one that can be used to graph surfaces in 3 space. So let's follow this link here, and I invite you to follow along. It's sort of similar to Desmos for the setup about how you want to enter your functions over on the side. But as we see, the display right here is this 3-dimensional plane. So the XY axis is this red and green axis down here, where we can see that's where we would normally think about how we want to graph our curves. But then this blue Z-axis is sticking up and we get 3-dimensional space. So it's kind of fun. What I want to do is I want to start by just kind of looking straight down on top of it. So it looks kind of like our normal XY axis. And if I do the input over here, how about like a standard line, like y equals x plus 1, for example. So if I just did like a standard line, like y equals mx plus b, it's a little bit hard to see. So let me go to my settings and maybe I'll turn the color like a darker blue color. Okay, so hopefully you can see that right there. That looks like y equals mx plus b, nice little line with a y-intercept of 1 and a slope of 1. But that's only because I'm looking straight down from above. If I tilt this and look at it in 3-dimensional space, this line is actually a plane. So if I tilt it, we can see that if it keeps extending all the way through the Z component, it's actually a plane. So if I'm looking straight down on it, yeah, it looks like a line on the XY axis, but it's extending into this other dimension. And it's just so cool to be able to play around with that kind of stuff. And so I would just invite you to play around with this. It's kind of fun to play around, but maybe if I delete that and try like 3x plus, I'm just making something up, 3x plus 2y minus z equals 4. I don't know. So that's just some other plane kind of cutting diagonal through all of these different axes. And that's just a way that we can visualize a plane in 3-dimensional space. All right, interesting, very, very interesting stuff. What if we did something a little bit different than a line? Let me delete that one. How about y equals x squared, like a parabola? And I'm going to change the color of that one again, kind of like the dark blue color to help us see it. Okay, so this one has a little bit of trouble trying to see the parabola if I'm looking straight down on the XY axis like that. But if I tilt and look at the 3-dimensional space, that definitely looks like a parabola, but it's slicing out and popping out off the page. Okay, so we've got this 3-dimensional looking parabola kind of thing. And we can just continue to mess around with this. And what if I wanted to write this as like x squared plus y squared equals z. Oops, that's in the exponent equals z. And you can get all kinds of crazy shapes. So you can get this like paraboloid kind of cone shape looking thing, all kinds of stuff. I mean, this is like a paraboloid. I mentioned a few of the other types of things, ellipsoids, paraboloids, hyperbolic paraboloids, all kinds of crazy things that you could start graphing on there. Let's see, what if I even wrote that as like z squared? Does that get weird? All right. So anyways, 3-dimensional, all kinds of interesting applications. And this is just a huge topic. You could really start going pretty crazy with graphing all kinds of stuff. And so I just wanted to get a visual aid here. If this seems a little bit scary, don't worry, I'm not going to be going into detail with this kind of stuff. It's just kind of for fun so that we can see all of these different options for graphing in 3 dimensions. Okay, so yeah, just kind of playing around there, just 3-dimensional shapes. Okay, so I invite you to play around with GeoGebra. It's fun to just kind of play around with this, but I don't want to scare you and make you think that we're getting into any kind of crazy stuff here. This was pretty much just some background information for, trying to visualize 3-dimensional graphs and graphing with 2 separate independent variables. Okay, so yeah, don't worry, I'm not going to have you do any of those crazy kinds of graphs. I just wanted a little bit of a visual exploration there. So in the next video, we're going to talk about partial derivatives. We want to find out derivatives, but if there's multiple variables involved, there's an interesting thing that we have to do to analyze pretty much like one variable at a time. Okay, so I'll make a new video to pick up on partial derivatives.